Hello everyone, and welcome to another FRQ. This FRQ we're going to be focusing on kinematics, so let's just get right into it. Okay, this FRQ is really interesting. There are a lot of different parts about this FRQ that I really like, so let's just get started. Very first part, determine the speed of the dart just before it strikes the block. Okay, so to do kinematics, the most important part is the information that you're given. Most of the time, they're going to give you a bunch of things. So the way I like to do kinematics equation is I just kind of write out what do I have and what do I know. So to calculate the speed of this dart, all they're asking is what is the speed of the dart, which is the horizontal component of the dart, right? We can't just take the this diagonal because this is vertical plus horizontal, and that's what makes it diagonal, right? We just want the straight horizontal component. So I'm gonna just draw this out real quick. So this is 10 meters per second, and this is 30 degrees. So how can we figure out the horizontal component? Well, we just have to use a bit of trigonometry to figure out this specific length. So to do this, all we're going to do is we know that if this just happens to be the hypotenuse and this is the opposite, then this must be the adjacent. So that being said, we're just going to use cosine theta, which is equal to the adjacent divided by hypotenuse. And then just by simply solving for it, we multiply our hypotenuse over, and our final answer should just be adjacent, which is equal to the hypotenuse times cosine theta. And all we have to do now is plug it in. So this is 10 meters per second times cosine of 30 degrees. Make sure your calculator is in degree mode. If it's in radian, you're going to get it wrong. And then we're going to get 8.7 meters per second. So notice how I added the unit. Make sure you don't forget your units, otherwise you're going to take off the point. And that's part A, pretty straightforward. So let's move on to part B. Okay, part B, calculate the horizontal distance d between the launching point of the dart and a point on the floor directly below the block. Okay, so if we notice anything about this projectile motion is it's a parabola, and just so happens that the parabola highest point is where the block is. So what does that tell us? Well, in a parabola, the highest point is when the velocity of the y component is equal to 0. Because as you notice here, the object is moving higher and higher and higher, but once it reaches this point, it begins to go lower and lower and lower, lower, lower. So that's how we know. Okay, so basically all we have to do is we can figure out when the velocity of the y component is equal to 0, and then using that time, we can just take our horizontal speed, and then with the time, we can figure out the distance. So let's do that. So just write out the kinematics equations. The velocity of the y component final is equal to the velocity of the y component initial plus the acceleration of the y component times t. So what are these variables? Well, we don't know what this one is yet. Actually, we do. What I just said was it's 0, right? So we can cross this out, let that equal to be 0. Now, what about a of y? A of y is gravity. Gravity is always in the y component. So as we know, gravity is going to be a negative force in the scenario because it's pointing in the opposite direction that the projectile wants to go. So for this case, I'm just going to write it as negative 10. And Vy initial, do we know what Vy initial is? Well, using a similar case in part A, we can just do this line, or I guess it's kind of like right here, right? Which is basically just the opposite. And if you use SOHCAHTOA, which is sine, excuse me, sine theta is equal to opposite over hypotenuse, with the opposite being what Vy is going to be, Vy initial is going to be equal to, right? So Vy is basically just going to be 10 meters per second times sine of 30 degrees, right? So now we can start solving. So right now we have zeros equal to 10 sine 30 degrees minus 10t. So let's just move over our stuff and solve for t. Negative 10 sine 30 degrees equals negative 10t. And t, once you divide negative 10 over, you should get about, I believe, 0.5 seconds-ish. That's what I have, around there. I think they would take anything around 0.5 to like 0.51, so that's around it. Okay, so now we have the time, right? But the question is asking for the time. The question is asking for the horizontal distance. So we're going to use this equation, which is basically just the velocity times the time to see how much distance we get. So we're just going to take our velocity, which we saw for up here, 8.7 meters per second times t, which is just 0.5 seconds. And notice how this seconds is in the denominator and this seconds in the numerator, canceling out the seconds, leaving us with just 4.4 meters because these are matching units. And that is part B. Okay, so now let's move on to part C. Part C, calculate the speed of the block just after the dart strikes. Okay, this is quite an interesting question. Basically, immediately what I'm guessing is it's going to be a momentum question because we have the initial and we don't know the final just yet. So let's get it. P initial is equal to P final. So always make sure to write this formula down. I can't stress it how many times you just write this formula down and you can get a point. So this is one of the easiest ways to just get a point on the AP exam, right? So let's just write Pi is equal to P final, right? And what is momentum? Momentum is basically just the mass times the velocity of an object, right? And if you have multiple, then just add the two, right? But if you notice that the momentum of the dart exists because there's speed and mass, but the momentum, the initial momentum of the block doesn't exist because while it does have mass, it doesn't have any speed. So there is no momentum there, right? So the initial is basically just going to be the mass of the dart times the velocity of the dart. And here it says the mass is about 0.02 kg, and we know the speed of the dart because we have it right here. We just calculated it in our previous part, so I'm just going to use that. Okay. Yes. Okay, this is right. Okay, and then what we're going to do now is we're just going to set equal to our P final. So what is our P final? Remember that it is the mass of the object multiplying by the velocity of the object. However, in this collision, the two objects collide and stick to each other. So that means we have to account for both the masses of both the dart and the block. So let's add the mass, 0.02 plus 0.1 times the velocity of it. So we don't know what the velocity final is, and that's what we're going to solve for. So when just multiplying and then dividing it over, we should get something about 1.4 meters per second. And that is the answer to part C. Okay, now moving to part D. So this is where it gets complicated. Calculate the angle theta through which the dart and block on the string will rise before coming on. Okay, let me just draw this part out again. So as we see, this is the block. And here is like the projected version of the block, right? So if we draw a line and make a triangle, we can find that this is just a triangle, right? So if you notice, this distance should be a little bit higher than this distance. And this right there, this distance is what we're going to call H. This I'm going to call L. And L basically stands for the length of the string, which happens to just be 1.2 meters. So this is going to be equal to 1.2 meters. Okay, and this is also 1.2 meters. However, this component is not 1.2 meters because we have to use trig here. So here's theta. Just using some basic trig, this will be 1.2 cosine theta, right? And we're basically trying to solve this theta. So first, let me write out the energy, right? So we're going to have the kinetic energy initial plus the potential energy initial, and then this is going to be the finals of them. This is the finals of them, and notice how the dart has no potential energy, right? There's no potential energy because it starts at the bottom, and so we can just cross this out. And this has no kinetic energy because in the question it does say it comes to rest. And if something's not moving, there's no kinetic energy. So cut that out. So all that's left is 1/2 mv squared, which is equal to mgh. Okay, so now we're like, okay, we have mgh. What is h though? Because h isn't just 1.2 meters. And even if it was 1.2 meters, how would we solve for theta? So this is where we're going to use trig once again. Basically, we know that h is the difference between the height of this point and like this point. I didn't really draw this quite well, but I want you to understand that this, where the block is, so like this is the height component of that block, right? And the actual string should be just a little bit longer, because if something basically the whole vertical component moves to the side, so the actual height of the object is just slightly shorter than if it was resting. So you got to kind of like think about that, like think about this thoroughly before you move on. Because if I have an object, right, so this is where the lowest point, right? But if I move it slightly, it's the distance between here and my thumb isn't the same as here. It's less than. So that is what h is going to represent. So let's solve for h. So h, we can just figure that out by taking this vertical component of the red and then just taking this and then taking the difference of it. So as we know, this one is the longer one, so that's L. And then we just take the vertical component, which is 1.2 cosine theta, or L is just 1.2, so I'm just going to write it in terms of the L theta, right? So we can just rewrite this. I'm just going to simplify this to 1 minus cosine theta. And that is what we're going to replace with h, because that is what h is equal to. So let's rewrite this equation. 1/2 mv squared, which is equal to mg L1 minus cosine theta. Okay, let me show you this. Okay, so now let's just simplify this. Just divide, so the m's can cancel out because there's m's on both sides. Divide the g, divide the L, add 1, and then reverse everything. So this should just be 1 minus v squared divided by 2 GL, and then take the inverse of cosine to get theta by itself, cosine -1, which is all equal to theta. And when you plug this into the calculator, just plug all the constants in, you should get about 24 degrees. And that's the answer for part D. Quite complicated, but very doable. Okay, part E. The block then continues to swing as a pendulum, simple pendulum. Calculate the time between when the dart collides, when the block. Okay, basically what they're asking is, it's really just a pendulum if you think about it. A pendulum is just something that is like a ball, and it just kind of swings back and forth, right? So this is just a block, right, with the dart in it, and it swings here, and it swings back, right? But as you know, if we're trying to find like the period, right? So that's what it is, the time. A period is basically like a full cycle, right? Back and forth, right? But it didn't go back and forth. It went like halfway, right? So if we just take the simple equation, the period is equal to 2 pi square root L divided by G, where L is the length of the thing, right? Then we should be able to find this pretty easily. So let's just do 2 pi, and then this is 2 pi 1.2 divided by like 10, and this should give you about 2.2 seconds, right? But remember, it's only half of it, so you actually have to divide this by 2, and the final answer is 1.2, sorry, not meters, seconds, and that's your final answer. So that's it for E. Pretty straightforward. Now let's do part F. Okay, part F. In a second experiment, a dart with more mass is launched at... Okay, so basically, all it is same speed, right? Same angle, pretty much same everything. The only difference is the dart has more mass. So what does this mean? Well, this means that the dart is going to have more kinetic energy, right? Because 1/2 mv squared, right? The kinetic energy includes mass, right? So it's basically more mass is more kinetic energy. So it's going to shoot, hit the block, and swing farther because it has more energy to transfer into it, right? So it should go to a higher height. So theta should increase. Okay, would the period of oscillation after the collision increase, decrease, or stay the same? Well, if we look at the formula, the period is basically just 2 pi square root the length of the thing divided by g. And the mass doesn't affect any of that. Gravity will always be the same constant, and we're not changing the length of the block to the roof. So this should stay the same. And that was the 2015 question 2 FRQ. I hope you kind of understand my thought process and how I did all these problems. And if you have any questions about what I did or how I did it, just leave it in the comments below. And I hope to see you in another video. Peace.